So we're going to continue on here with chapter 2, and last time we talked, a lot about sort of waves and electrons transitioning from one energy level to the next. We talked about sort of the Bohr model of the atom, which results in, really describes nicely sort of the lines that we see in something like hydrogen. It does sort of fall apart when you got a lot more electrons happening. But we talked a lot about sort of elements and the idea of sort of this quantized energy. And the idea of quantized energy is, again, pretty much electrons, for example, which is really the focus of what we're talking about here. Electrons will gain enough energy to go from one energy level to the next. Again, they'll never sort of find themselves between energy levels or anything like that. So that's, again, sometimes like the stair sort of example. Again, as we talked about last time, if you're walking up or downstairs, I guess, you do have enough energy, obviously, to get from one step to the next. Again, some people can maybe do 2 steps and so forth, but you never sort of find yourself in the middle. And that's really the idea there, that quantized energy. These particles, like electrons, again, will do transitions that get them from one energy level to the next. Bohr had more of an orbital or planetary sort of model, and it doesn't really hold up, as we'll talk about today, and we sort of move away from it. But what elements do is, again, they do really give off what are referred to as line spectrum, these distinct lines at specific wavelengths that correspond really to electrons, being transferred from one energy level to the next. When electrons go from a lower energy level to a higher energy level, that again is endothermic, so energy needs to be put in there. The electrons need to sort of gain that energy. Again, kind of like what you did with your flame test yesterday. Clearly, all those samples gain a lot of energy as you stuck it into the flame. And that's going to allow those electrons to be excited to higher energy levels. They will kind of bring themselves back down because, again, everybody wants to be in a lower state of energy. That's sort of the preferred situation for pretty much everything. So in order to do that, to come back down in terms of energy does need to be released, which is sort of an exothermic type process in that situation. We talked about calculating certain things like wavelength and frequency, and we could use sort of this equation that we saw last time, which again, this is the speed of light, and that's a constant. That's that 3 times 10 to the 8 meters per second. This is our wavelength. Again, usually in meters. That is our frequency. And reciprocal seconds are sometimes a hertz is given, which they are equal to each other. So it is sort of a one-to-one relationship between those two. We also saw energy is equal to h times the frequency, h here being Planck's constant, which is our 6.63 times 10 to the minus 34 joule seconds, also a constant. And then obviously this is a frequency, which would be 1 over seconds, again, in this case. We can put both of these guys together, as we talked about, basically solving for frequency. So you could also very commonly see this version of that equation, where it's the energy is equal to h times c, which those are both constants, divided by the wavelength. And that allows you to figure out the energy of a wave. If you simply just know the wavelength, you could pop it into there. The top two numbers are obviously a constant. This guy does need to be, once again, in meters for everything to cancel out correctly in terms of the units. We then talked towards the end there a little bit about the transitioning of electrons from one energy level to the next. So we can also calculate the energy associated with those transitions. And it is the change in energy is minus 2.18 times 10 to the minus 18 joules, 1 over n squared final minus 1 over n squared initial. This is what is referred to as Rydberg's constant, the 2.18 times 10 to the minus 18. N is the principal quantum number, as we talked about. And again, that is a fancy way, basically, of saying energy levels. So basically, the energy level is the N number, and it does have values of basically 1 through 7. 1 is what is referred to as the ground state. and that is the guy that is the lowest in energy, is the closest to the nucleus. Anything above that, n equals 2, 3, 4, 5, however many, 6 or 7, those are considered excited states. Those are higher in energy, and they are further away from the nucleus as well. Any questions on any of that stuff we talked about last time there? Okay, so I think we left off on an example where we could do some of these calculations. And by the way, we can tie, as we talked about last time, this equation into our H times V, and then obviously into this guy as well. So those all kind of go together. So while we do some of these calculations, make sure our calculators work. Let's super zoom in case you missed it. So 3 different problems here. We want to know what is the color, but more importantly, we want to do some calculations here for these guys. So for each of these, for A, B, and C, let's calculate the wavelength in nanometers. Let's also calculate the frequency. And let's also calculate the change in energy that occurs as those electrons transition from those different points. That should give you some good practice with your calculator there. So it takes a few minutes here, or several minutes. And for each of these electron transitions that occur, calculate those 3 things. Once again, nano is 10 to the minus 9. Let's take a look, see how you're doing on these. So we're doing some electron transitioning. So we definitely want to use some of the formulas that we've seen. So we have our change in energy minus really Rydberg's constant here, 2.18 times 10 to the minus 18 joules, 1 over n squared final state there, 1 over n squared initial. We also, like we talked about just a second ago, we could tie this guy into the couple other ones, which is E is equal to H times the frequency, and also coming this way, E HC over the wavelength. So again, we could kind of use all these sort of formulas here together to calculate the 3 things that we're looking for, which is obviously the wavelength, the frequency, and the change in energy. And this will be pretty much all the calculations we do today in lab. So obviously in this case, the place to start would be with the first one here, since pretty much all we're given is the states or the energy states at which these electrons transition from. So that is where we'll start. So we'll start with the first one, which is 5 to 2, looks like. So n equals 5 to n equals 2 here. So clearly we are dropping in energy, right? Coming down. So we will do our change in energy equals minus 2.18 times 10 to the minus 18 joules. Our final state is the 2. So 1 over 2 squared is 4. Minus our initial state, which would be 1 over 5 squared, which would give us 25 in that case. And if we put all that in here, we end up with minus 4.58 times 10 to the minus 19 joules. That would be our energy associated with this transition for that particular electron. First off, any questions on that there? This also makes sense, as we talked about. Once again, our electron is higher in energy. It is dropping down, which means it needs to release energy. And we do see that we end up with a negative value for energy, which is exothermic. It means it is being released. So again, as we talked about last time, you do want to keep the negative there. So you want to make sure you keep the negative for the energy value. But at this point, you do want to really ditch the negative when you go into calculating for wavelength or frequency. Again, those should be positive numbers, so you don't want to keep the negative when you kind of continue on with the calculation. Otherwise, obviously, you'll get a negative wavelength or frequency. At this point, we really could go with the this relation. We could go with either one, really. At this point, we'll all start with the wavelength. So I'll calculate the wavelength by using this formula here. To solve for the wavelength, we're going to multiply the wavelength to the other side and divide by the energy, which would give us that the wavelength is equal to hc divided by the energy. And that would give us our Planck's constant, which is a constant value you always have, 6.63 times 10 to the minus 34 joules times seconds. You could also do then the speed of light, 3 times 10 to the 8 meters per second. All that would be divided by our energy here. And this is the part where we do want to get rid of the negative so we don't end up with a negative value. So we're just going to use really just the same number. Again, as the energy is conserved, so overall the energy change, either positive or negative to go up or down, is going to be the same. So what that does then is the joules will cancel, the seconds will cancel, and we will be left with just meters as the unit that's left over at that point. We want to make sure that we do use our exponent button, obviously, on all these. So 6.63 exponent negative 34 times 3. That is not my exponent button. I want to hit the right one. There you go. To the 8. All right. And we're going to divide it by our 4.58 to the negative 19. That is going to give us a wavelength of 4.34 times 10. That's a lot of zeros. 1, 2, 3, 4, 5, 6, 7, minus 7 meters. Since we did want the wavelength here in nanometers, we'll do our conversion. And that's where we use our Nano Conversion. That is 10 to the minus 9 meters and 1 nanometers. And that will turn that basically into 434 nanometers at this point. Any questions on that calculation there? Yeah. What's that? Okay. We're going to do a couple more here. Where you exactly lost on? That is Planck's constant. That's a constant value. That is also a constant value. So there's no calculation on those. You just use the numbers. This number came from the first calculation, the energy part. Yeah. Other questions? Okay, at this point, we have the wavelength. We also have the energy. So we can throw back to our older equation as well. You could just use this one if you like to figure out the frequency, since we have the wavelength. And once again, C is a constant value. So if we solve for the frequency here, it would be C divided by the wavelength. And this, once again, C is a constant. So you have that, which is 3 times 10 to the 8 meters per second. The wavelength here, we want to make sure that we use the one with the correct units. We do not want to use the nanometers because they will not cancel because the top guy is in meters. So we do need to use, obviously, the one here in meters so everything cancels out correctly. So we do want to divide this by 4.34 times 10 to the minus 7 meters. That way, when we do that, the meters and the meters will cancel out. Again, if you use the nanometers there, you will be off, obviously, by a factor of like 10 to the minus 9. At this point, we will divide those two numbers. Once again, make sure you use your exponent button. 3 exponent button 8 divided by 4.34 exponent button minus 7. Going to give us a 6.91 times 10 to the 14. The units here are actually reciprocal seconds, yes, which is the correct units for frequency. Reciprocal seconds, which again is a hertz. Any questions on any of those parts there? Yeah. Yeah, so frequency and wavelength should always be positive. Energy can be positive or negative. And again, as we talked about, positive means it's endothermic, it's absorbing energy. Negative means it's exothermic. So you definitely want to leave the negative sign if you get one for energy, which you will every time an electron goes from higher to lower. It's going to always be negative in terms of the energy. But you do want to get rid of it for the other parts of the calculations because you should never have a negative wavelength or frequency. So, and again, you could do that because really the amount of energy that is being given off by the atom in that change in sort of the different energy levels would be the same amount of energy that would be needed to be gained to go upwards. So we could use the positive version there to get the same positive wavelength or frequency. Do you have a question? No, there's not. So I was going to kind of mix it up and do it that way the next time. But yeah, so there's a couple of different ways you get there. You should, depend on rounding, but you should pretty much get the same number no matter which way you go. Yeah. Other questions? Yeah. Yeah, I think you should be okay. So as long as you got like 6.9ish, if you're talking about like that number or something like that, or 4.5 or 4 points, it should be okay. Yeah. Personally, when I do it, I like we talked about when we were talking about sort of measurements and all that. I personally will usually just take kind of like the whole number on here and just kind of keep going with it, and it's kind of rounded at the end and stuff like that. But you should be okay if it's just a small difference in rounding. Other questions? Okay, so let's take a look at the next one, which is 4-2. So we're going to go on this one from 4 to 2. So once again, we will open up with our change in energy for that transition, minus 2.18 times 10 to the minus 18 joules. Our final is 2, so that's 1/4, which is 2 squared, minus our initial, which is 1/16, which is 4 squared. And if we do that there, I personally will do the stuff in the parentheses first. So 1 divided by 4 minus 1 divided by 16, then times it by 2.18 exponent minus 18. And that will get us here a negative 4.09 times 10 to the minus 19 joules. Again, once again, we get a negative value for the energy, which again does make sense as we are transitioning down from the 4th energy level to the 2nd, lower in energy. So we will we'll go with what the question was on the left there. We can at this point hit the frequency first because we do have the energy. So we could use E equals H times the frequency if you want to kind of go that route first. At that point, H once again is a constant. So that would be our Planck's constant, 6.63 times 10 to the minus 34 joules times second. Our frequency here is what we're looking for, and that would equal our positive 4.09 times 10 to the minus 19 joules. So if we rearrange that, the frequency would be our energy divided by our H in this particular case. So putting those numbers probably a little bit better here. We'll go with 4.09 times 10 to the minus 19 joules divided by 6.63 times 10 to the minus 34 joules seconds. Once again, the joules will cancel, leaving us 1/seconds for our units. And if we do that there, we will yield something in the ballpark of 6.17 times 10 to the 14 reciprocal seconds. And that would obviously be our frequency at this point. At this point, now that we have our frequency, again, you have really two options. You could still go back into this equation and use it like we did on the first one there to find the wavelength. Or you could also use this equation here and solve for the wavelength. Again, they both should give you the same answer, regardless of which way you want to go. So since we mix it up here, we'll go with this way for this time. So we will solve for the wavelength, which will be the speed of light divided by the frequency. And once again, the speed of light is a constant 3.0 times 10 to the 8 meters per second divided by the frequency, which we just calculated there, 6.17 times 10 to the 14 reciprocal seconds. In this case, our seconds will cancel out, and it will leave us our wavelength in meters in this case. So 3 to the 8 divided by 6.17 to the 14 gets us a 4.86 times 10 to the minus 7 meters, which once again, we could use our conversion to go to nanometers, which is 10 to the minus 9 meters is a nanometer. And that will get us a 486 nanometer as our wavelength in this case. And again, if you took kind of the same route that we took the other problem, you should end up with pretty much the same numbers. So if you went this way first and then went into here, you should get up the same answer. Any question on any of those there? Okay, so the last transition was, I think, 3 to 2, if I'm not mistaken. Yep, 3 to 2. All right, so let's take a look at 3 to 2 here. So our electron starting on the third energy level, ending on the second energy level. So obviously that's the only piece of information we got. So much like the other ones, we do need to start with sort of the Rydberg equation here. Change in energy minus 2.18 times 10 to the minus 18 joules. In this case, our final was the second energy level, which would then give us our 1/4 because we squared 2, minus our initial, which would be 1/3 squared, which should be 1/9 in this case. At this point here, we take 1 divided by 4 minus 1 divided by 9, and then multiply it by 2.18 to the minus 18, giving us an energy change of minus 3.03 times 10 to the minus 19 joules. Once again, it does make sense. We hit a negative value there for our energy as our electron is again coming down in energy. Now, if this electron was going up in energy, the only difference here would be what's in the parentheses would switch and pretty much the sign would change is the only difference that would happen, and we would end up with a positive value if we were going in the opposite direction. Yeah. Any question on that one there? All right, so let's see. Let's go with the wavelength next. Why not? So E is equal to HC divided by the wavelength. Once again, rearranging this gives us that the wavelength would be HC divided by E, and that is found by multiplying the wavelength to both sides, then dividing E to both sides. Gets you there. Putting in the top two, which once again are constants, so 6.63 times 10 to the minus 34 joules times seconds are 3 times 10 to the 8 meters per second, divided by our energy, which once again we're going to turn into a positive number so we don't hit any type of negative wavelength. And once again here, the joules will cancel, seconds will cancel, and we will be left with meters there. And I guess I need a calculator for that probably. All right, 6.63 minus 34 times 3 to the 8 divided by 3.03 to the minus 19. Gonna yield us a wavelength here of 6.56 times 10 to the minus 7 meters. Once again, transferring it into nanometers, which is 10 to the minus 9 meters is 1 nanometer. And remember that that 10 to the minus 9 is basically 1 times 10 to the minus 9. And when you put that into your calculator, if you need to put the 1 in, that's basically, again, what you would put in there. So we'll divide that by 10 to the minus 9, and that will yield me a 656 nanometers. At this point, we can get the frequency using this equation, or we can, again, like we did on the previous one, use this equation because we have both of those numbers. So it is just your preference, whichever way you want to go. So I'm going to use this one and get the frequency. So the frequency here would be C divided by the wavelength, and that would be our constant. 10 to the 8, there you go, meters per second. Once again, though, when we do use this version, if we're going to use it, we definitely want to make sure we're using our meters here so we're not off by a factor of any type of units there. So we want to do that one. That way the meters, once again, will cancel out correctly. And that will get us some type of number. There we go. We'll go with 4.57 times 10 to the 14 reciprocal seconds in this case. Or obviously you could also just write reciprocal seconds like that, S to the minus 1 if you like. Or you could use a hertz if you like that, even better. Any question on any of those calculations? We will do thousands of them coming to the lab here today of these guys. Yeah. All right, so let's go back and take a look at really sort of what we are looking at in terms of what the question was. I think there are some other parts of the question. First off, we're looking at which one results in the longest wavelength, right? So our longest wavelength we had 434, we had 486, and we obviously have 656. So this would be our longest wavelength, right? In terms of energy, that guy then should be the highest or lowest in energy. Should be the lowest in energy, right? So it had 3.03 to the minus 19. This guy had 4.09, which is more, right? And this guy had 4.58, which is more. So this guy also over here had the shortest wavelength, right? Should correspond to the highest energy. And again, we do see that as well. And also should have a higher frequency, this guy, right, than the guy on the other side. And then we could go back and take a look at our guy there for our colors. So if we go back to our visible part of the spectrum, which is here somewhere, I think. Did I pass it already? I passed it. There's pickle. There we go. So we had, what do we have there? We had 4, what was the first one there? Was it 486? 454, something like that? Yeah. So that would be over here, probably in the kind of violet range. Was it 486, the other one, right? So probably over here in the bluish range. And then the last one was it 6 something? Yes. So orangey yellow, maybe, or orangey red, maybe, if it's in the 6 something range, would be over here. Yeah. Any questions on any of that there? So those are definitely all the calculations for sure you need to know, and you'll get way more practice here in lab today because you will be looking for lines and basically having to calculate all those things there. All right, let us continue on then. All right. There it is, blue, green, and orange, red would work, I think. There we go. All right, so let's talk a little bit about the idea of, and we did before, sort of the dual nature of light and matter, and the idea that, again, particles like electrons, again, can have wave-like functions, and particle and waves could have particle-like functions. And deBroglie basically came up with this sort of proposed idea. There's actually a second, this should be there, by the way. And he said that basically he predicted that the wavelength of a particle is inversely proportional to its momentum. And he talked a lot about sort of the idea of standing waves, if you will. So standing waves, is kind of like something that is tied down like a guitar string, right? If you pluck it, right, you will see the wave, right? If you kind of pluck the string. But it's basically anchored down to the guitar, right? So it can't really kind of go anywhere. So it's sort of like a standing wave. And that's sort of an idea, if you kind of think about it, like our positively nucleus and our electron. So even though electrons are particle and they're sort of randomly moving, they are sort of tied to sort of the nucleus by that attractive force. So they get that sort of wave-like character, as they're moving around, and they have some of the wave-like functions. So we can figure out what is sometimes referred to as the deBroglie wavelength. And that is the wavelength in meters is what that is. And that is times h, which is our Planck's constant, and that is our 6.63 times 10 to the minus 34 joules times seconds. Now, if you remember at the end of the last chapter, we saw a relationship that a joule is equal to a kilogram meter squared second squared. And that is basically where this comes from. That is the joule part of it. And that's why it's missing a second still there. So that's where all those sort of units come from, is the relationship that a joule is a kilogram meter squared second squared. While that's really important, and it really doesn't change the calculation for H or the number for H, it does change the bottom part here that instead of getting the mass in grams, you do need to get it into kilograms. So again, the units cancel out. So if you're trying to figure out the de Broglie wavelength for a particle, you do need to get the mass, you know, not normally, we oftentimes think of it in grams, but you do need it in kilograms so that it will cancel out. So that's a really important relationship here between those two. The velocity would be in meters per second, and that also is how this all cancels out. So if we just sort of look at the units for this guy here, the wavelength will equal our kilogram meter squared second squared times the seconds divided by kilograms and meters per second. So when everything starts canceling out, a second here and a second here takes care of both of those. A kilogram here and a kilogram here takes care of that, and a meter takes care of just one of those guys, and it leaves just the meters left over. So the good news is you could still write up on top there's, 6.63 times 10 to the minus 34 joule seconds, as long as you remember that the bottom part where the mass is does need to be converted to kilograms, and then you should be in good shape. Everything will cancel out, and you'll always be left with meters. The other thing that's important as well, sometimes the velocity is not given to you in meters per second, so you may have to do some type of conversion to convert it to meters per second, again, to make sure that, everything cancels out. You could have a velocity like miles per hour, right? Kilometers per second, something like that. So you want to make sure, again, that you get that velocity into meters per second here. So this allows us to sort of apply wave type function to things like particles. So let's take a look here. Calculate the de Broglie wavelength of an electron that's traveling at 2.65 times 10 to the 6 meters per second. And we'll use this, which is nicely converted to kilograms for you already. So I guess that's nice. So take a second there and calculate what you come up with. All right, so let's take a look here. So we're going to calculate the de Broglie wavelength. So that is going to be our h divided by our mass times our velocity here. In this case, everything's actually in the right units. So we do have the velocity in meters per second. In this case, we do have it in kilograms, the mass. If it's not, obviously, you do need to do those conversions like we talked about. That would get us basically here 6.63 times 10 to the minus 34 joules times seconds, which once again, the joule part of that is a kilogram meter squared second squared, divided by our mass, which is in kilograms. So that's good. And our velocity there, which is in meters per second. I scribbled on it. I think it's a 6, right? Meters per second there. All right. So once again, unit-wise, because a joule is a kilogram meter squared second squared, that's where the kilograms cancel. Our second there takes care of both of those. And again, that takes care of just one of the meters at that point. That's going to give us 6.63 to the minus 34 divided by 9.11 to the minus 31. Personally, I would hit equals at this point and then divide it one more time, 2.65 exponent 6, maybe 6, there we go. Looking like here, 2.75 times 10 to the minus 10 meters in this case would be the de Broglie wavelength for an electron. That is a large number, a small number? Pretty small number, right? So it should be a little bit higher in energy and stuff like that. So should be moving around pretty good. Any questions on that calculation? Yeah. The kilograms cancel out from, because a joule is equal to a kilogram meter squared second squared. So we got the kilograms there on the bottom and on the top, and that's where they cancel out. Yep. Other questions? So the good news is, kind of like I said, it's really still Planck's constant, so you could just roll with the number that you find on the handout or whatever. But the one thing you do have to remember is to do that conversion, because a lot of times masses are given grams and stuff like that. So you got to make sure that you get that. Otherwise, you'll be off again by a factor of like 1,000 or so. Yeah. Other questions? All right. So hopefully they agree with me here. That's good. All right. So as we talked about sort of, I think at the very end last time, and we were talking about sort of Bohr's model of the atom, that planetary model, we talked about the idea that, we sort of moved away from, are moving with this type of thing away from sort of that Bohr's model of the atom where we have these nice orbits where everybody's moving around in pretty circles and stuff like that, to really a more quantum mechanical model, sort of a wavelength, wave model type of idea. Like what deBroglie came up with, a particle like an electron can have some wave-like characteristics. The next sort of major thing that sort of moved us away from the idea of these orbits and again into this idea that, electrons are really found in places what are referred to as orbitals is what's known as Heisenberg's uncertainty principle. Heisenberg's uncertainty principle is really the idea that pretty much you don't really know how a particle like an electron, for example, is moving at any given point in time. And really, the more you sort of learn about its path, if you will, the less you kind of know about its location, and sort of vice versa. The more you sort of understand about where it's sort of at, the less you know about how it's sort of traveling. And that's really what this equation is here, is basically to change the position, and the change in momentum is greater than or less than, greater than or equal to h over 4 times pi. We're never going to use this in terms of a calculation, but this is the basis behind the idea of electrons really moving in sort of a pretty random pattern about the nucleus. And really what we move away from is sort of Bohr's idea of, well, I know there's these different orbits and I know, hey, my electron's moving around in this orbit. And at some point, if I stuck my finger there, it's going to come around at some point and hit me, right, and move around in a circle, sort of constantly moving. So we move away from sort of this idea of sort of Bohr's model to really this more quantum mechanical model of where electrons are sort of randomly moving at any given point in time. And what that sort of does for us, or what they sort of moved into, is the idea really of a sort of probability, and the probability of finding electrons, where you would find electrons within the atom. And that's really what these orbitals really are. They're sort of probability maps of theoretical places of where inside an atom you would find electrons sort of housed. And as we talked about, sometimes there's the greatest sort of possibility of finding electrons should be near that nucleus because it is positively charged. Electrons are negatively charged. So there's going to be an attractive force between those. And the highest probability would be found, kind of near that positive charge. As you sort of fan out from the positive charge at some distance, there's still a probability of probably finding an electron maybe floating around in there. But there's less of a probability of sort of finding it and that farther away from the nucleus than closer away to the nucleus. So we get these sort of probability maps, and this is for like an s orbital, for example, and you can see, I guess it did come out pretty good. You could kind of envision the nucleus there in the center, and you can see the darkest sort of probability there is from found near the center. And as you sort of fan out, the probability really starts to decrease in terms of finding an electron out in that area. Doesn't mean there's not an electron there, but you have obviously a greater chance of finding that. And that's really what this graph is showing. The probability of finding an electron, for example, is very high the closer you are to the nucleus. But again, as you sort of move yourself further away from the nucleus, there's less of a probability of sort of finding one out there. And what that led us to is really the idea of sort of orbitals. So we move away from the idea of orbits like we had in sort of Bohr's model to this sort of really theoretical ideas of orbitals as really probability maps of where we find electrons within an atom and where they are found. So the relative sizes of orbitals are difficult to define. There's a guy named Schrodinger who had a bunch of equations, and if you ever take physical chemistry, you do a bunch of calculus with those type of wave-type functions. And they basically, again, are sort of how these orbitals sort of came about and the idea of where we find them. So hydrogen has a 1s orbital, which is a sphere, kind of like what we just saw there, where the highest probability of finding electrons, again, is near the nucleus there. So why don't we take a look? Actually, we'll come back to this. We're going to get a little bit further up in the notes there. We're going to look at orbitals here, and we'll come back to what we just skipped there here. Where is that in your notes here? There it is. So let's talk about orbitals and sort of their shapes and where we sort of find them. One type of orbital is an s orbital, which is what we see here. And there's really only one type of s orbital. And by the way, orbitals, which are these sort of theoretical places where we do find electrons within the atom, they really could only hold 2 electrons. So any individual orbital can hold a max of 2 electrons. So any individual orbital, no matter what type of individual orbital it is, the maximum number of electrons that you can put in there is going to be 2. So when we talk about s orbitals, they actually start on all energy levels. So they start really at the n equals 1 energy level, and we'll see why that is in just a second. But every energy level will have an s orbital. The first energy level is what's referred to as a 1s orbital, and because on the first, 2s orbital, 3s orbital. And you can see that as it sort of goes from one energy level to the next, the size or the shape of it remains the same, but the size gets a little bit bigger to obviously accommodate all the electrons that are kind of in there. The next type of orbitals that we talk about are p orbitals, and these guys first really do appear on the second energy level is where we first start to see p orbitals appear. There's actually 3 different types of p orbitals, and the 3 different types is a px, a py, and a pz orbital, and that's what we see here, px, py, and pz. And it's basically different arrangement in 3-dimensional space. One's like on the x-axis, y-axis, and z-axis. That's happening here. And it's also sometimes referred to, as you can see, a little bit different shape. It's sort of a teardrop sort of shape, kind of the highest probability of finding electrons is sort of in this area here, because the nucleus is probably fissioned right about there. So again, kind of the highest spot on both of those lobes of the p orbital is found right there. Now, because there are 3 different p orbitals, these are sometimes referred to, all 3 of them together, as the p subshell or p sublevel. Depends on your book. I think perhaps our book uses shell, but some people use level instead of shell. And that would be all 3 of these guys together. Each individual orbital could hold 2 electrons. So this guy could hold 2 electrons. This guy could hold 2 electrons. This guy could hold 2 electrons. That means if you took the entire subshell, you could fit 6 electrons max if you put them all filled, all the 3 different d orbitals, 2 into each, 2, 4, and 6 electrons total if you fill them all together. Any questions on that there? Here are our d orbitals. D orbitals start to appear on the 3rd energy levels where they really start to appear. And there's actually 5 different types of them. And once again, all 5 of those different types are basically what are referred to as the d subshell, or again, sublevel. And Ds kind of look like, for example, kind of 2 Ps put together and like a p orbital and a donut over here. But once again, each of these could hold 2 electrons, which again, if we max out our d orbitals, all of them together, the subshell could hold a maximum of 10 electrons to fill the subshell. And these are, again, our sort of probability maps. And again, you can see a lot more darker areas here. around where we would anticipate the nucleus being, sort of in the center there. And as you can see, as you sort of fan out from there, a little less of a probability of sort of finding those, not as dark as you can see really near that where we would envision the nucleus sort of being in the center there. Lastly, in terms of orbitals, it is the F orbitals that we sometimes deal with. F orbitals occur on the 4th energy level, and there's actually 7 different types of F orbitals, and here's all 7 of them. You can see they kind of look like some D's put together in each of these cases. Once again, each of these individual orbitals here could hold 2 electrons, which means for our F subshell, if we fill it up, we are looking at a maximum of 14 electrons in this case. Yeah, it's sort of bonding and anti-bonding is sort of thing. So they kind of cancel each other out. So there's a positive and negative sort of lobe that happens in those cases now. So these are the sort of important ones to know for electron configuration, which is sort of where we're headed. But before we get to electron configuration, we're going to sort of talk about how we kind of know, how many orbitals there are and where they're located and what energy level we sort of see these different types of orbitals. So let's go back to what we skipped ahead from and come back to that slide there. Okay, so what allows us to understand with this sort of quantum mechanical sort of idea of orbitals and all this kind of stuff is what is referred to as quantum numbers. So there's actually 4 different types of quantum numbers. And the first one we talked a little bit about, and that is N, and that is what is referred to as the principal quantum number. It is basically the energy level. And as I mentioned before, N could have values of 1 through 7, basically. The next sort of quantum number is L, and that is the angular momentum quantum number. And that's sort of the shape of the atomic orbitals, sometimes called the subshell. That is basically going to tell you, are you dealing with an S orbital, a P orbital, a D orbital, an F orbital? So that's what L will tell you. A specific value of L will tell you, okay, these are S orbital, or this is a P orbital, or this is a D orbital that's happening. Now, L could have values of 0 to n minus 1. So the values of L range from 0 to n minus 1. The next quantum number is the magnetic quantum number, which is m sub L. And that is sort of the orientation in 3-dimensional space of those orbitals. So for example, like we just saw with our p orbitals, right? There's a px, a py, and a pz. This number here will tell you really 2 things. It will tell you the orientation in 3-dimensional space, but it will also tell you the number of orbitals there are in a subshell. And m sub L can have values of minus L to 0 to plus L, all kind of whole number integers. So it goes from negative whole number to 0 to positive whole number. So it will tell you, again, sort of the number of orbitals there are. It will also tell you, for example, where the electron is in which particular orbital in 3-dimensional space as well. The last one here, which is actually down the road, I think on your handout on slide or 2, is what is referred to as the spin quantum number. And that is m sub s. And the spin quantum number has basically values of plus a half or minus a half. And that is really the spin on the electrons. So electrons have their own spin. They're affected by sort of magnetic fields, electrical fields. And they can have sort of positive spins and negative a half for the spin. For the most part, we represent a lot of times, and we'll do this when we're talking about electron configuration and stuff, we represent sort of electrons and orbitals with like an arrow, for example. And if the arrow is pointing in the upwards direction, and that is usually the first electron that goes into an orbital, it would have basically what is referred to as plus 1/2 spin. The second electron that goes in typically will go in the opposite direction and sort of pointing down, and it is what is referred to as negative 1/2 for a spin quantum number. So any electron that sort of goes in is sort of technically kind of pointing upwards, if you will, has a positive half spin. Any electrons that go into an orbital that pointing downward has minus 1/2 spin. So those are the 4 quantum numbers that we have. So for example, let's take a look as to how we could use these to understand really, and what we're really talking about here is, as you may be familiar with, electron configuration, like a 1s2, 2s2, 2p6, all those kind of things. How we kind of get that, you know, what everybody is on each of the energy levels. So let's take a look at these guys here. Let's start with, if we went to n equals 1, which is the ground state, basically the lowest energy, right? So this is the ground state. Is obviously the closest to the nucleus. So if we had an n is equal to 1, our L value, now L is 0 to n minus 1. So clearly if n is 1, 1 minus 1 is 0. So the only possible value you could have for L is 0. A value of L of 0 represents an s orbital. So what that is telling us is when we go to the first energy level, the absolute only thing that we will find there on that n equals 1 is a s orbital, and is referred to as a 1s orbital. Our m sub L could go from minus L to 0 to plus L. In this case, since L is equal to 0, the only value for m sub L that we could have is 0, right? Lastly, the m sub S here could be plus 1/2 or minus 1/2, because we could put in that orbital 2 electrons. First one could go in, and that would be plus 1/2. Second one will go in, and that would be minus 1/2. So those are the 2 possible spins you could have. You have it spinning upwards or spinning downwards. These would be the only 4 possible quantum numbers for basically the first energy level. And by the way, we see here we have just 1 number for m sub L, which is why we have just 1 orbital and 1 orientation in 3-dimensional space. Any questions on that there? So let's see what happens when we go to sort of the second energy level. If we go to the second energy level, that would mean that n is going to equal 2 here. I'll try to do it on this page. So if n is equal to 2, that means when we go to L, L could have values of 0 to n minus 1. So n minus 1 in this case is 1. So L could have values of 0 and 1 in this case. So 0 and then n minus 1 gives us 1. So those are the 2 possible values for L in this case. This tells us that on the second energy level, we once again have a s orbital, because we have an L that has a value of 0. So if we go to our second energy level, we definitely have a 2s orbital. The 2 means it's on the second energy level, and it's a s orbital. A value of 1 for L represents the p orbitals. So that tells us that the p orbitals appear here on the second energy level, and that is why earlier we said that s's begin on the first energy level and p's begin here actually on the second energy level. Now, for every value of L, you could have some m sub L values. So my value of L, which I did just like above, would have an m sub L of 0 as it goes from minus L to plus L. That is why on the second energy level, much like the first energy level, there is only one s orbital, right? Because there's only one number that is there. If we are now talking about the p orbitals, which are an L value of 1, my L value of 1 would give me an m sub L value of minus L, which would mean minus 1, to 0, to plus L, which would be plus 1 in this case. First off, that is how many numbers right there? That is 3 numbers, right? And p orbitals, p subshells have 3 different p orbitals. So what those numbers tell me is, first off, on the second energy level, there is a p orbital, and there is a 1, 2, 3 different p orbitals, which is our px, our py, and our pz. And that is what minus 1 represents, 0, and plus 1 represents for the m sub L number, is what those guys are in that order. So you can actually get really specific and know exactly, what orbital that electron is sitting in based on, knowing that this first guy is the minus 1, the 0, and the plus 1. Any questions on that there? By the way, the m sub s for each of these would be plus or minus 1/2. Right? This guy would have an m sub s of plus or minus 1/2. And again, in each of these orbitals that I drew here, we could put 2 electrons, one going upwards, one going downwards when we do that. Any questions on that there? Okay, so why don't you try all the possible quantum numbers for an electron on the n equals 3 level. All right, so take a couple minutes, see what you come up with. Okay, let's take a look. Starting with n equals 3, we have possible values of L in this case that can go once again from 0 to n minus 1, which means we could have values of 0, 1, and 2. Obviously, the 2 being 3 minus 1 gets us to 2 in this particular case. This is telling us that on the third energy level, we once again see s orbital there. We also see p orbitals there. And now this is where we will actually start to see our d orbitals there. So an L value of 2 would represent a d orbitals or subshell. Now, for each of these, we obviously can go through individually here. The rest of it, our m sub L for our 0 will be 0 like we did previously. Also, obviously, having an m sub s of plus or minus 1/2. For our L is equal to 1, as we did on the previous example, that will give us an m sub L that goes from minus L, which would be minus 1, to 0, to plus 1, which was our 3 p orbitals that we talked about, our px or py and our pz. Each of those orbitals can have a spin of plus or minus 1/2. So we'll just focus here on the one that we didn't do sort of before. And that would be our L value of 2, which would represent our d orbitals. That gives us an m sub L that runs from minus L, which would be minus 2, to minus 1, to 0, to plus L, which would be plus 1 and plus 2. Again, this tells you really the orientation in 3-dimensional space of those orbitals, but more importantly, it also we see 1, 2, 3, 4, 5 numbers there, and that is why we have 5 different d orbitals and a subshell for d's. Each of those individual d orbitals could also obviously have an electron that is plus or minus 1/2 in there. So what that tells us is, again, we already did our n equals 1. We have our 1s, our n equals 2. We had our 2s, and obviously our 2p. When we get to our third energy level, we again have our s orbital present, which would be a 3s orbital. We have our p orbitals present, which would be our 3p. And now we have our d orbitals present, which would be 1, 2, 3, 4, 5, which would be 3D. Any questions on that there? And in terms of numbers, it would run, this way, 0, plus 1, plus 2, in terms of, their orientation in three-dimensional space. That is also why we talked about there that the f orbitals don't really appear till we get to the fourth energy level, because if we ran our n is equal to 4 in this case, that would give us L values of 0, 1, 2, and now 3, as 4 minus 1 would get 3. Once again, that would be our s orbitals, that would be our p orbitals, that would be our d orbitals, and that would be our appearance of our f orbitals on the fourth energy level. And if we did m sub L for just 3, it would go from -3 to -2 to -1 to 0 to +1, +2, and +3. And if you count up all those numbers, that is the 7 f orbitals that we have in obviously different orientations in three-dimensional space that happen. So when we get to our fourth energy level, again, 4s, I'll squeeze them together, 4b, 4d, and then obviously ran out of room, but imagine there's 7 of them there, 4f, obviously with 7 orbitals that are happening at that point. Any questions on sort of quantum numbers? So yeah. You would. So if we had n equals 5, you would have an L value of 0, 1, 2, 3, and then 4. So that's an S, that's a P, that's a D, that's an F. And you might be asking, what is that? And they're very creative. They just go alphabetical at that point. Yeah. So it's like a G, I think, comes after, right? A, B, C, D, E, F, G. And then the next one would be H and so forth. We never get into these guys in something like electron configuration. We sort of tap out there at the Fs. But basically that is sort of the designation that you would do, just kind of go alphabetical after that point in terms of their destination. And obviously you would obviously have -4, basically -3, -2, -1, 0, +1, +2, +3, +4. So however many that is, I think 9, if I counted that correctly, you would have sort of that many orbitals would technically be there. But we don't really have any elements that sort of reach there. They sort of, again, sort of die out there at the F sort of orbitals and stuff like that. Other questions? So this again is really the basis for electron configuration. And when we write electron configuration, as you might have done in the previous class, there's really kind of 2 things that's really important in terms of writing electron configuration. And that is sort of the order at which they go in. And in the case of an electron or an atom where there's really only one electron, all the orbitals on a particular energy level are subshell. And since we're talking about some of those terms, let's just make sure here. When we talk about a level or a shell, we're talking about every orbital within that's on a particular n value. So if we wanted to know the maximum number of electrons on the n equals 2 level or shell, how many electrons would that be? If we filled it up. It would be 2 there, right? And 2 on each of these guys. So that would be 2, 4, 6, 8 electrons, right? If we maxed it out, you could put a total of 8 electrons max on that entire shell. And that's different than, say, the first energy level, right? You could only put, obviously, a maximum of 2 electrons in that particular case. If I want to know the maximum number of electrons on the 3p subshell, how many electrons would that be? Anyone? It would be 6, yes? So that is these guys here, right? All three of those p orbitals together is a subshell or sub-level. Each one could hold 2. And that would be 6 electrons in that particular case. How about a 4d orbital? What is the maximum amount of electrons? That is the trick question. It is 2 electrons, because a 4d orbital could be this guy could hold 2, could be this guy could hold 2, could be this guy that holds 2. Any individual orbital can only hold 2 electrons. If I said how many electrons could the 4d subshell hold, the answer would be 10, right? 2 into each, it would give you 10. So those are some terminologies that sometimes used with this stuff. Levels or shells basically is the entire n number, or everybody that's on that level in terms of energy. Subshell is really, all the p orbitals together, all the d orbitals together, all the f orbitals together. We really don't call S a subshell per se, because it's really just one orbital by itself. There is no others. So it's all those guys together. And then obviously any individual orbital would be just one guy by itself. Now, when we do get multiple electrons that happen, what ends up happening is, for example, here, if we look at the n equals 3 level, all of those guys are exactly at the same energy level. Everybody that's at 3 is perfectly equal to each other in terms of energy. But what ends up happening when we get multiple electrons involved, obviously they're all electrons, so they're all negatively charged, got a lot of negative guys kind of flying around near each other. They really don't want to kind of be near each other, but they can't really escape per se. What ends up happening is there's some shifting that occurs in these different orbitals, and some of these 3s orbital or 3s orbital, 3p orbitals, 3d orbitals, they sort of move in terms of where they are in terms of energy. And the major difference sort of happens as we go from, for example, the 1s orbital ends up being lower in energy, obviously, than the 2s orbital. 2s orbital ends up being less in energy than the 2p orbital. That is then the 3s orbital, then our 3p orbital. And now you might be tempted to go, it is going to be our 3d orbital. But actually what happens when we get multiple electrons involved, it's actually the 4s orbital is actually the next lowest in energy, followed by the 3d. And that's kind of the major sort of swing that occurs. These sets of orbitals are really close in energy to begin with, and they actually switch back after electrons go in. But as electrons go in, they do have this sort of difference in the energy of these orbitals. And that's really important because electrons basically go into the atom like you're walking stairs. They go lowest energy first and then go to the next and then start filling as you kind of continue up. So there is an order that occurs, and there's an easy way to sort of figure out how that is or figure out the order. And it's by knowing what we just talked about, which is on the first energy level, there is basically just the s orbitals. On the second energy level, that is where the p orbitals come from. On the third energy level, that is where the d orbitals come from. And on the fourth energy level, that is where the not the s orbitals, the f orbitals, there you go. Kind of like s, but not so much. F orbitals begin. And pretty much you could just fill in the numbers underneath it, like 2p, not p, 2s. There we go. Try that again. I'll learn the alphabet here soon. Let's try that there. All right. 2s, there we go. 3s, 4s, 5s, 6s, 7s, right? N goes from 1 through 7, so that is where the 7 rate comes from. And then fill this in. This would be 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 6d, 4f, 5f. Now, this is sort of the order at which electrons fill the atom, and we always start at the very top here, where you start. And then once you fill that, you zigzag back to the other end of the arrow, zigzag back. And if you do this, you will get the correct electron configuration. As you can see there, the 3p to the 4s. now to the 3D, to the 4P, to the 5S, and you just kind of keep zigzagging back and forth. If you know this or how to recreate it like I just did there, and not too bad a shape there, and you know that the S could hold a maximum electron of 2, the P subshell is 6, the D subshell is 10, and the F subshell is 14, you should be able to write any type of electron configuration that you would need to do, which we will do, I guess, on Tuesday, as Monday is a holiday, I believe. Yes. So we will lay it up there for now. Any questions on any of that there?